So the first problem I will be covering today is a problem from Polish Olympiad 2017 grades. So in this problem there are n students in the class and they are in a line. The teacher has to assign grades which satisfy some conditions. So if for two pupils V and U, if V's athletic index is greater than U's, then V's grade cannot be less than that of U, as that would be unjust. So it must be at least that of U, or it can be equal also. For two pupils V and U, if V is after U in the line, then he should not get a grade which is less than that of U. So basically, this means that if the students are standing in a line, say A1, A2, A3, and so on till AN, then the students which are later in the line should not have the grade which is worse than students earlier in the line. So this means this is a non-decreasing sequence. So the grade 1 is grade less than equal to grade 2, grade 3, and so on. The other condition is that these AIs are the athletic indexes of the student. So AI is the athletic index of the ith student in the line. And now if AI is greater than AJ, then GI also must be greater than equal to GJ, as if it's less than that would violate the condition. So did everyone get the problem statement, the two conditions? Okay. So now the teacher wants to maximize the number of different grades they can give while observing the above rules. Also, each time the class takes place, two pupils swap their places. So there are like queue updates, and in each update, two pupils like the ith and jth one will swap their places. So after each update, you need to answer the maximum number of different grades the teacher can give. The constraints are given here. So n is up to 1 million, and the number of updates is up to 300,000. There are also some subtasks. So you can like fit quadratic subtask and get the first two subtasks. So now I will explain. So now we have already seen that this is non-decreasing sequence. So G1 is less than equal to G2 is less than equal to G3. So now we need to maximize the number of different grades. So like if we are increasing the value of a grade, say GI plus 1 is greater than GI, then we should have GI plus 1 equal to GI plus 1. So it's either plus 1 or the same. Like this is optimal. If we increase by 2, it does not affect like the number of distinct grades we can give. So it's not needed. We can get an optimal solution without increasing by more than 1. Now suppose there's a student AI which is who is earlier in the line and age is after. Now suppose AI is great, like let's suppose I is less than J, so I is earlier in the line, and now let's take AI is greater than AJ. Now since the athletic index of the ith student is more, the grades of the jth student must not be more than that of the ith student, since that would be unfair. So this means that GJ is less than equal to GI. However, since I is less than j, this means that gi is less than equal to gi plus 1 is less than equal to gi plus 2, and so on is less than equal to j. So now these two inequalities we get. First is this, that gj is less than equal to gi, and the second one is gi is less than equal to gj. So this means that gi is in fact equal to gj. So did everyone get this? Okay. So now the problem is how to efficiently find the maximum number of distinct grades. So we have some segments, like if AI is less than AJ, we have a segment if AI is greater than AJ and I is less than j, we have a segment from I to j, which means that gi equal to gj. So we cannot increase the grade in this interval. And now if we like get all the intervals and merge them, say these, so these all are equal, and say like for example here's another interval, these are all the intervals possible in some example, then these are all same and this is one segment, so we get two grids. So now I will show like how you can get a nice representation of this. So suppose gi is less than gi plus 1. This means uh, that let's say g20. Now one possibility is that the g1, like these are the grades, so let's look at their athletic indexes. So one possibility is if that a1 to ai form a permutation of 1 to I. One thing I have to mention is that in the problem it is given that every student has distinct athletic grades, so it's a permutation. A is a permutation. So now let's say this is a permutation of ai, or if the first I elements are the permutation of the first I numbers. Now in this case we can give a higher grade to gi plus the I plus 1 student than the ith student. This is because this would not violate any condition of the this form, since ai we need ai is greater than aj and I is less than j to violate a condition. However, all the numbers in this prefix are less than any number in the suffix. The suffix will have numbers I plus 1, I plus 2, and so on till n. So we can give a different number here and we can increase the index. So now let's look at the this is not a permutation. So suppose that the first I elements do not form a permutation. That means that if this is not a permutation and there are I elements, there must be an element greater than I. So there must be an element like greater than I uh, in the athletic indexes. And since there are only I elements, we do not have all the first I elements. So there must be an element x is less than, let's take it to be m, which is the maximum element. M is greater than I. So there must also be an element x is less than m, which is not in this prefix. Since these are like at least one number is not in the prefix, so we have that m is here and x is here. This is a split into two parts: the first I elements and the last n minus I elements. So the maximum element here is greater then the minimum element here. There's an element which is less than the maximum element. This means that the grades of these two must be equal by our previous property, that if ai is greater than aj and I is less than j, then all the numbers in between have the same grade. So this means that gi and gi plus 1 are the same. So basically, we need to count the number of prefixes which are a permutation. So we for if we look at the first I elements, if A1, A2 to AI is a permutation of 1 to I, then we can assign a different grade between the I and I plus 1. So like for I is less than equal to n minus 1, we count the number of prefixes possible, count, and obviously we need to add 1 in the beginning, as the first element is also there and we are not increasing there, like the G1 element, which is 1. So we need to count the number of prefixes of length up to n minus 1, which are permutation, and we need to add one. Now notice that the first 10 elements always form a permutation. So instead of adding plus 1 and doing for less than equal to n minus 1, we can just count the number of prefixes up to length n, which are permutations. So did everyone get this part? Okay. So now, if we do this in a brute force way after every update, then this would get 32 points, I believe, or even lesser it might get. So now we need to find a fast way to maintain the number of prefixes which are permutation. So now notice that if, see, this is not a permutation. If the first I elements do not form a permutation, this is not a permutation, then there must be an element x is less than or equal to I, which is not there. So this means that x must be outside, like say here. And now this cannot be a prefix which can be counted, and we have to somehow disable this prefix. So what we do is, for an element x, if see, this is at the jth position, if x is less than j, say x, these are the first x elements, then notice that all the I from x to j minus 1 cannot be permutations. X to j minus 1, if you notice that these ranges do not have x and they must contain x. So these are not permutations, and so we can add 1 to all the segments x to j minus 1. And at the end, we do this for every element. If x is at a x, the value of x is less than its position, we do this everywhere, and we count the number of prefixes which have a value of 0. So we do a plus 1 in this range. So did everyone get this part? How we maintain the number of prefixes with value was 0, and those will be the answer. Okay. So now we can do this efficiently with the segment tree, or we do it with the segment tree and not a binary index tree, because we need to maintain the number of elements which are 0. So what we will do is, in each node of the segment tree, we will maintain minimum element and count of minimum in a segment. And we have point updates, since we only need to like swap ap and aq. So we have a update where we change an element. So we change this to aq and this to ap. So we do 2 point updates to the segment tree. So now if there's an element x at the jth position, x is less than j, then for the range x to j plus 1, add 1 in the segment tree. And now for the whole tree, you see the minimum element. Like if it's 0, we get the count also, count of 0. And if it's not 0, then the answer is 0. But that actually never happens, since the first 10 elements always form a permutation. And you never add anything to the nth element. So you get the minimum of the whole tree as 0, and you also get the count 0. So did everyone get this part, how we maintain a segment tree of the minimum element and its count? I can also show the code for it. So we have range, have range add updates, where we add one. We do have range updates actually. We add one to a ranges, and we need to find the minimum element. So what we will do is, like while updating, if the range current node lies entirely within the range, we need to add an element, a number to it, and so the minimum changes and the count of the minimum never changes. And now while merging two nodes, we take the minimum out of the minimum of both, and if like the left node has the same minimum as the whole tree, we add its count, and similarly for the right node we do the same. So now for updates, we just need to maintain the elements in an array, and we just swap them at the end, and we update the yes. Okay, I will repeat it. So we need to maintain the number of prefixes which form a permutation, right? And so if we can like count, disable the prefixes which don't form a permutation, we can just count the remaining ones. So for example, if this is not a permutation a1 to ai, there must be an element x is less than I which is outside the first I elements. So now if x is outside the first I elements, this cannot form a permutation. So now notice, like if x is at a position like greater than x, say j greater than x, it's here. Now if we see the prefixes x, x plus 1, x plus 2 and so on till j minus 1, these are not valid prefixes. See, because the first x elements don't have x, the first x plus 1 don't have x and so on till the first j plus 1 element also don't have x. So we need to add 1 here and disable this. So we only need to count the elements with value 0 at the end. Did you get this part, why this range get disabled? Okay, so now we only need to count the number of zeros, and as I demonstrated, it can be done with a segment tree, maintaining the minimum element and the count of the minimums. So did you all understand the complete solution of this problem? Okay, like if you have any doubts, you can ask. Okay, so now I will give you a different problem. Suppose you are given a directed graph. It can be cyclic, no, like it can have cycles as well. So there are like no specific conditions. You have a, like I'm just drawing a random example, and there are n nodes, and you need to find if between two nodes a and b is there a path of length k. So if you can traverse k edges and reach b from a, and k can be very big, like up to 10 to the power 18, n is say let's say 300. So now the queries of the form, can you reach, like not queries, but we have a number k and we need to find the pair of nodes such that we can reach from one to the other in exactly k moves. Exactly k. We cannot take like less or more. So did you all get this problem statement? Okay. So like we are given two nodes a and b, and we need to find if there's a path of length k from a to b. So say like this is a part of length 2. So for k equal to 2, this is satisfied. Let's say for these two vertices, there's a path of length 2, this one, and so it is satisfied for k equal to 2. So now if k is very big, can we still solve the problem? The graph can have cycles also. N is up to 300 and k can be as big, like say 10 to the power 18. Okay. So now what we do is we try to form a matrix representation. So for the first matrix, we let aij equal to, let's say this is of parts of length x. If a path of length x exists from I to j, so this is a matrix of zeros and ones. And now if k equal, like this is of x, right? If a path of length x, so now if x equal to 1, this is adjacency matrix, the normal adjacency matrix. And we need to be able to find this matrix for like greater x also. And now suppose we have another matrix, but this is for y. So we have 1 0 ai j equal to, if a path of length y exists from I to j. So first matrix is if a path of length x exists, and second is if a path of length y exists. So now notice what happens when we multiply two matrices. So if we multiply two matrices Aij and Bjk, what we get is a matrix, let's say Cik, the like the ith row and kth column in this is summation of product of Aij into Bjk, and J can vary. So these are n by n matrices. So we can vary J, and this is standard matrix multiplication. What happens when we multiply two matrices? So Cik is summation of Aij into Bjk. Did you all get this part? Okay. So now if we need to check if a path of length x plus y exists, then there must be from I, there must be a intermediate vertex, let's say L, and then another vertex j, such that there is a path of length x from I to L and a path of length y from L to j. So for any x plus y, if a path of length x plus y exists between I and j, there must be a path of length x from I to L and a path of length y from L to j. For they must exist some L for any L. So now notice that in this matrix, the first one, AIL equal to 1 if there's a path of length x, and A Lj equal to 1 if there's a path of length y from L to j. So now if we sum up overall, if we sum up the calculation, we can see if there's an a, like if this is greater than 0, this means that Aij is greater than 0 and Bjk is greater than 0 for some j. This must hold true if the value is non-zero. So this means that we can find an intermediate vertex to go from I to k and x plus y moves. So did you all get this part? And we also like min this by 1. We just need to check if a path exists and not to count the number of paths. Okay. So now I will give you a problem. You are given a directed graph, like explaining the previous technique gives a huge hint on how to solve the problem. Also, one more thing I want to mention is that if you have a matrix, if you need to calculate, so basically this whole matrix multiplication, if you see, you multiply, this is, let the adjacency matrix be A, adjacency matrix. So this is A to the power x, this is A to the power y, and this actually is ax plus y. So basically what you need to do is you need to calculate the kth power of an adjacency matrix. Now you remember, if you remember how to do binary exponentiation. So like generally people have to calculate a to the power x mod something, mod say 1e9 plus 7 for a number a, and there's a binary exponentiation trick where you can do this in log n operations, log x operations. So similarly we do here also. So what we can do is we can calculate this for like powers of 2. So we calculate a square, a to the power 4, a to the power 8, and so on till a to the power 2k, 2 to the power k. And now if we want to represent any number, we can represent it as sums of powers of 2, like looking at the binary exponentiation, and we can multiply the log n matrices. So you have to do around like 2 log max k multiplications. So 2 log key and each matrix multiplication, so it's n by n matrices. So this will take, the summation will take n cube time. So this is n cube into log max k. So did you all get the how to do the binary exponentiation? We can calculate a to the power 2 to the power k from a to the power 2 to the power k minus 1 into a to the power 2 to the power k minus 1. So did you all get this part on how you can do log n multiplications to get the kth power of a matrix? Okay. So now the problem is you are given a graph, directed graph, and there are k explorers. You have k explorers a1 at positions a1, a2, and ak. All are distinct. K is less than equal to n. And each day the explorer sets out on a trail. So like if they are on a vertex, they will go to the vertex or go to a vertex which has an edge leading from the original vertex. So if they are at I and there's a edge say here, they will follow exactly one edge every day, and so they will go say here, and then say there's an edge here, they can go here and so on. So they must traverse exactly one edge every day, and you need to find the minimum number of days such that after like z days they can meet on a common vertex. So you have to find the minimum number of days such that. So formally, the problem is find minimum z such that there is a common vertex such that there is a path of length z from all the original vertices. Like say you have part of length z. So did you all get the problem statement? This is also a Polish Olympiad problem. So this one is the problem POI 2019. The constraints are n is up to 300, 250, and like there can be any edges. And also the condition is given that every node has at least one outgoing edge. So you never get stranded at an island. You always move every day. And now you need to find the minimum z such that you can reach any edge. Like there's a subtask in this. I will explain like an easy subtask. It is possible to remain in any shelter. This means that for every edge there's an every node there's an outgoing edge which comes to itself. So they are self loops. So now in this you can stay at a vertex also. This is the easier subtask. And so what you need to do for the easier subtask is for like say a vertex x, you want them to all of them to meet at x after some days. So you from a1 you find the path length c1, let's say a2 you find the path length c2. This can be done using BFS easily, shortest paths, which will be n cube, since you need to run the BFS from every node. And now notice that if you can reach the final node in C queries, then you can also reach in C plus 1 or C plus 2. Since you can like this is a self loop, so you can just stay in the same node and then reach, or like reach first and then stay in the same self loop. So now what in this problem we just need to calculate the maximum of all the distances, and for all the common nodes we can calculate the minimum over all of them and we can get the answer. This gets 30 points. But the harder problem is when there may not be self loops. So did you all get the subtask? Like if you have any doubts you can ask. Okay, problem link I will send. So now the harder problem is I will explain it using the previous trick. So now notice that if like the K explorers can reach a node in exactly say J moves, they can reach J moves, everybody reaches a common vertex. Then they can also reach a common vertex in J plus 1 moves. Say like that, this common vertex, they can just go any random edge, all of them. So you can also get a J plus 1, J plus 2, and so on. So if you can like binary search the answer. So you have to binary search if for a given X, can you reach a common node in exactly X moves starting from these? You have to reach a common move like every player. goes passes exactly x edges, and you have to reach a common node. So you have to check for a fixed x if it's possible. So did you all get the binary search part, why binary search would work? If you have any doubts, you can ask. Okay. Hello. Yes. Just like if you have any doubt, you can ask. Like if you have any doubts related to this problem, like for other doubts, you can message me later. So like, did everyone get this problem? How we can binary search on X? Now the difficulty remains in how to check if we can reach a common vertex in exactly X moves. So now we will use the trick from earlier. In this, we were able to check for a fixed k if it's possible to go from any node to another node in exactly k moves. So now we do this for x. We get the matrix for x, ei equal to 1 if path of length x from I to j. And now what we need to check is that, say, from a1, a2, and ak, if there's a node j such that there's a path of length x from j. So we need to check the k values of the matrix and check if there are one. For like every common node we check, and so like in order n square time we can check if there is a node. And so now notice that our complexity here will be something like, for calculating the matrix we are taking like n cube into log, n cube into log time, and now we are also binary searching, so this is actually log square. So this won't pass, this may not pass the time limit, and this would get lesser points. So did everyone get this part of the n cube into log square solution? How we invoke the matrix from earlier to solve the problem? Okay. So now we need to see how we can optimize this from n cube into log. Like we need to go to n cube into log. And so now notice that if we maintain the powers of 2, the matrices which are powers of 2, so a to the power 1, a to the power 2, a to the power 4, and so on till a to the power 2 to the power k. And so now in the initial matrix we only maintain a to the power 0. And now what we do is we do something similar to binary lifting. So now notice that in the problem statement it's given that the number of explorers is greater than 1. So like we can't finish the problem in 0 moves. We need to make at least one move. So we start with a to the power 0. We multiply a to the power 2 to the power k into it and see if, like, after this many moves, if it's possible. If it's possible, we don't multiply it. And if it's possible, we just multiply it. So like this is similar to binary lifting. So if 0 is, so we are at current, and we are at the current power of 2 is 2 to the power j. So now if it's possible to reach in, if it's not possible to reach in cur plus 2 to the power j moves, then we multiply it. So current matrix equal to current matrix into a to the power 2 to the power j, if not possible. So in this way, and if it's possible, we don't multiply it, since we always need to keep under the answer. And at the end, we will be just below one below the answer. So this is basically just binary lifting. So let's say if 5 is the answer. So we multiply it by 8 and see that this is possible, so we don't multiply it. Now we multiply by 4 and see that this is not possible to reach in 4 moves, so we just multiply it. Now we at 4, we multiply 2, like we go in decreasing order of powers of 2. So if we multiply 2 here and we see that we can reach here, so we don't multiply it. Now we multiply 1 and see that we reach here, and now we don't multiply it actually. So we get 4 in the end, and we need to add 1 to get the minimum answer. So the minimum answer is 5. And now you are only doing log n matrix multiplication, so it's n cube log n the complexity. Did you everyone get the full solution? Okay. So now I will discuss the third problem for today. In this problem, you are given there is a hidden tree and a sequence a1 to an. Ai is the distance of the farthest vertex from node I in the tree. And now you need to determine whether such a tree exists at all. So n is at most 100. Although you can easy like the same solution works for a larger n also. So now you need to find if there's a tree which satisfies this. So I will give example. So, so suppose this is a tree. The farthest vertex from node 1 is like distance 2. So a1 equal to 2, a2 equal to 2, a3 equal to 3, a4 equal to 3, and a5 equal to 3. So did you all get this the problem statement? And you need to check if a tree exists with these values. Okay. So now notice that you can get the diameter, the length of the diameter of the tree. Suppose like such a tree exists, then the length of the diameter will be max a1, a2, and so on till an. So you this will be the length of the diameter of the tree. Now suppose this is the diameter of a tree. Let these vertices be a and b, and like let the length be like say x. And now notice that for a vertex, say a vertex in the subtree of one of the, like these are like x edges, and so x plus 1 vertices. So like let's say we have a subtree here. Now notice that we will show that the farthest node, so for a node I, max distance j comma I equal to max distance a comma I comma distance b comma I. So we can show that at least one of a and b or b is one the furthest node from any vertex. So now I will show this fact. So now suppose that say we have a node which is further away. So let this be in a subtree here, and let this be node I. And so suppose that the node is like outside of this subtree. So now notice that like if say there's a path of length x after reaching the root of this tree, like we split it into different trees. If there's a path of length x, these are also two paths, right? And if x is greater than max of the other p and q, say this is length p and this is q, then notice that this p is not the diameter, p plus q is not the diameter. You can delete q and add x instead, and x plus p is greater than p plus q, so this is not the diameter and this is not possible. And the other case is when this is in the subtree only, we don't go till the line and we like reach a node and then go down again. So now let's say, so we will compare two paths here. We'll draw it again. So now suppose this is not the complete tree, but so now suppose the farthest node is somewhere here, And now we will compare it to a path where we go up and to the maximum on any side. This is P, this is Q. And so now notice that the depth of any node here is less than equal to min PQ. So now suppose from this node we can go more than P steps, then we can just replace P and with this, and this would be a larger diameter. So the depth of any node here is less than equal to min PQ. So and now the depth here is less than equal to is I depth I plus depth of this, that is this be Z. So depth of Z, and now depth of Z is less than equal to min of P plus Q. So depth of I, now if you look at the other path, which is we go, this is actually the depth distance is less than equal to this, since we might actually break earlier also, like the LC might be lower. So in the worst case when it's on the line, this is the maximum value is depth I plus min PQ. And now notice that if we go on a separate part which depth I and plus max P comma Q, we will get a value which is at least this. So suppose we go up and we go here, we will get a value which is at least this. Did you all get this part? So now the main claim here is that the farthest node from a node is one of the points on the diameter. Like one of the farthest nodes is one of the points on the diameter. So did you all get this part? Yes, Shubham. What you are saying is very close to the answer, that we can put the maximums on the two ends. So now I will show a solution. Now we are almost done. So suppose we are given a path. We know the maximum value of the diameter is x. So the at the endpoints of the diameter, this is x. This is x minus 1. This is x minus 1. So like if the diameter length is like even, this is odd. Let's say odd. Then we get two nodes here equal, two nodes here equal, two nodes here equal. Now let's say if the length is like even, we get x, x minus 1, x minus 1, x minus 2, x minus 2, and x minus 3 here. So now we these like AIs with these values must exist. X is the maximum value of all AI. So now what we do is we remove these values from the set of A1 to N. We remove these values, and if we cannot remove these many values, clearly no tree exists. And now we are left with some values. So now notice that if x is a diameter, then the farthest node, so AI must be at least x by 2 ceiling. We cannot have it less than. Like I showed earlier, the farthest node is a point on the diameter. And so at least one of the values, say from any node, at least one of these two distances will be x by 2, right? So we cannot have value less than x by 2. And now notice that we can attach leaves here. So if we attach a leaf here, we get x distance. We get x minus 1 here, x minus 1 here, x here. So now we can show that for even x, let's say like, let me rephrase it. Let's say 2k. These are the AI values. So now if you write them down, you will get k plus 1. Then you again get k plus 1 and so on till 2k. I think I wrote down correctly. And now notice that you can add 1 here. And now notice that you have removed the maximum element. So all elements are at most 2k. So to get any number from k plus 2 to 2k, what we can do is we can just add edges here. So if we add edges to k plus 1, we get like farthest will be k plus 2. And like we can add as many edges. And so if all the numbers are in this range, we can do it. And similarly, we will handle the odd case also. It's very similar, and like I will leave it as an exercise to the reader. So did you all get this solution? How we can attach the remaining vertices as leaves to this path? I will also like show it on the example. So the example is 3 2 2 2 3 3. Okay, it has the Jamboard has run out of slides. I will just use this. So now I will just demonstrate it on the example. So we have 3 times 3 and this. So now the diameter has length 3. So we have 3 here, 2 here, 2 here. And now we need an additional 3. So if we add an edge here, the farthest node will be on the diameter only, this one. So this will, we can add a 3 here. The farthest node will have distance 3 and we can construct the graph. And similarly, we can do for every case. If you implement this properly, you can get order n or n log n implementation. Like they are like the constraints are very low, so you can pass quadratic or cubic solutions as well. So did everyone get this part, the final solution? If you have any doubts, you can ask. Okay, that's it for today. Thanks for attending.